Before I'm going to talk about net ionic reactions, I want to talk about what happens when you put an ionic compound into a solution. And the reason that we care so much about aqueous solutions and the reactions that happen in them is because we can do a lot of analysis with them. We can do qualitative tests, so we can test for the identity of a cation or an anion. We can also do quantitative tests where we measure for the concentration of an anion using a precipitation reaction. So if we take two solutions together, create a solid, we can actually go filter that solid out, weigh it, and then determine how much of an ion might have been present in the solution to begin with. And that's called gravimetric analysis. So anytime that an ionic compound dissolves into water, this is what happens. If I have sodium chloride and I put it into water, I just dissolve it. What I do is I actually separate the ions out, like this. All right, so I have sodium chloride. It gets dissolved into water. I'm going to produce sodium ions and chloride ions. So in the solution, what you actually have looks like this. It's not sodium chloride. It's just going to be the ions. And the negative ones actually should be bigger. So they're separated out, and you have these charged particles floating in the solution. So what can actually happen when you have an ionic compound dissolve into water is I could connect this to some sort of circuit with maybe like a light on it or a buzzer or something. So let's say this is a light, and the light will actually go off if there's a power source. And this is a very bad drawing of what I'm trying to describe. But basically, if you attach probes to some sort of circuit, because there are moving ions in the solution, you can actually conduct electricity. So they are called electrolytes. So if you have a large number of ions in the solution, it can conduct electricity, which is why it's called an electrolyte. It indicates that an ionic compound has completely ionized. And so anytime that we have an ionic compound that dissolves into water, it's a strong electrolyte. So all soluble ionic compounds are strong electrolytes. Also, strong acids and bases are strong electrolytes, because they will also produce a large amount of ions in the solution. So anytime that we have a strong acid, a strong base, and we're going to go over that in a later unit or at a later time, anytime that you have this or a soluble ionic compound, you have a strong electrolyte. That means that there are ions present in that solution and it can conduct electricity. All right, so a weak electrolyte is where you have only a few ions in the solution. So it can conduct electricity, but not as much as the strong. And weak electrolytes would include only slightly soluble ionic compounds, non-soluble, because what ends up happening is some of it will actually dissolve if you put enough water in there. So you will actually have some ions, but just not very many. And also weak acids and weak bases. So what will end up happening is if you put a weak acid or weak base, some of it will ionize and you'll have some ions floating in that solution, but you'll also have some molecules. So in this type of solution, you'll have some charged particles like this, but then you'll have no charges on the other ones. They'll stick together, they don't actually ionize, but you'll have a couple that do actually break off and ionize. So you'll have some ions in the solution. And this includes non-soluble ionic compounds or slightly soluble, weak acids, and weak bases. Non-electrolytes, no electricity is conducted, no ions are present. This is most covalent compounds. So what will end up happening is you have a solution of you have a solution and they're just molecules. The molecules will separate into the water, but They're just a whole unit with no charge. So there's no charge associated with these molecules. So most covalent compounds are non-electrolytes. All right, so when you have an ionic reaction, it's going to separate into its ions. So let's say that I have this, and it's being dissolved into water. Oops. If it's being dissolved into water like this, it just separates into its ions. So it's going to make strontium ions with a positive 2 charge, and also chloride ions. But you see there's 2 chlorines here, so there should be 2 chlorines on this side as well. So if you're asked to write out an ionic reaction like this, make sure you have charges, make sure you put your aqueous, and make sure that it's balanced. So if I have 2 chlorine atoms here, I should have 2 chloride ions here. All right, now weak electrolyte, what's going to end up happening is, yes, some of it will ionize. So this is a weak acid. So anytime I have a weak acid, it's going to create hydrogen ions and then something else. This happens to be acetic acid, so acetate will be produced. But not very much of it. And that can be indicated with this arrow here. You see how it's more towards this side? That means that, yeah, sure, some of it will break apart into ions, but most of it will not. Okay, and then a non-electrolyte would be any covalent compound. It'll separate into molecules, though the atoms don't separate, the molecules will, but not ions. It's not going to create an ion. All right, so when you have a precipitation reaction, which is double replacement reaction, you need to make sure that one product is insoluble, which is a precipitate. So you're going to use the solubility rules. Here are our solubility rules for soluble compounds. The ones with stars are the ones that you have to know. Everything else will be told to you somehow. So soluble compounds include group 1 elements and ammonium. So if it's anything with anything in group 1 or ammonium, it's soluble. So like if I have ammonium sulfate, well, it has ammonium, it's soluble. If I have sodium chloride, group 1, it's soluble. If I have potassium carbonate, has group 1, soluble. Okay. If it has nitrate, it is also always soluble. So silver nitrate, soluble, because I have nitrate in it. If it has nitrate in it, it is soluble. Hydrogen carbonates are usually soluble, so if it has HCO3 in it, it's soluble. If it has chlorate, it's soluble, so potassium chlorate would be soluble. Or barium chlorate would be soluble. Calcium bicarbonate would also be soluble. If it has a chloride, bromide, and iodide, those would be soluble, except if they're with these 3 ions. So silver bromide would be insoluble. Silver chloride, insoluble. Mercury iodide would be insoluble. But if I had sodium iodide, if I had barium iodide, those would be soluble. Sulfates are usually soluble except when they're with these ions. So silver sulfate would not be soluble. Sodium sulfate would, barium sulfate would, but not silver. Oh, I'm sorry, not barium. So another example would be potassium sulfate. So if I had lead sulfate, that's also insoluble. Calcium sulfate would be insoluble. All right, so now insoluble compounds usually contain hydroxide, except when it's with group 1 or ammonium, so sodium hydroxide is soluble, but lead hydroxide would not be soluble. Carbonates, phosphates, and chromates and sulfides are usually insoluble except when they're with group 1 or ammonium. So sodium sulfide is soluble, ammonium sulfide is soluble, but lead sulfide would not be soluble. Now, and also sulfides with group 2. So that means that it's sulfur bonding to something in group 2, like calcium. Calcium sulfide would be soluble. Barium sulfide would be soluble. All right, so let's look at this. What we're going to do with this is we're going to predict whether this reaction will actually happen or not. So we're going to predict the products and then check the solubility rules to determine if the reaction happens. So we identify the cation first, silver here, potassium here. Silver is a +1, then NO3 would be a -1, potassium is +1, bromine is -1. So the silver will switch places with the potassium and bond with bromine. Check your charges though when you put them together. +1, -1, they cancel. All right, so now potassium will bond with nitrate, -1, so +1, -1, they cancel. All right, so now we're going to look at our products. Well, right here, I have something with nitrate. Nitrates are always soluble, so I know this is soluble. So this is going to be aqueous. And then right here, silver bromide. Well, if I go back and check my solubility rules, bromides are usually soluble, except when it's with lead, silver, or mercury. So in this case, bromides are usually soluble, but it's with silver, which makes it insoluble. So this is going to be our solid. So the reaction does happen because I produce a precipitate. This is my actual product. Because what ends up happening with this, since it's soluble, is that as soon as it forms, it just breaks apart into ions again. Okay, so when we look at net ionic reactions, this is what we just did. We predicted we're going to make this and this. Well, what's actually happening is this. This is what's actually happening. This is the real reaction. Everything else is just a spectator. It's not really participating in the reaction. Silver plus bromide produces silver bromide. That's the only real reaction that happens here. Because when I make potassium nitrate, all that happens is it just splits apart again because it's aqueous. Okay, so when you're writing the net ionic reaction, you're going to write the balance reaction first, and then write the ionic reaction by taking everything that's aqueous and splitting them into their ions. Do not break the precipitate apart. So anything that's got aqueous by it, you break it apart. Anything with a S by it or solid, don't break it apart. And then you're going to take out ions that appear on both sides. So let's look at one. Let's look at this one. All right, so since we already predicted this one, we know that this is our equation is already balanced. So now everything with an AQ, we're going to break it apart. So it's silver with a +1 charge, AQ, and nitrate with a -1 charge. Do not pull this apart into nitrogen and oxygen. It's a polyatomic. Don't pull it apart. And this is aqueous, so I pull it apart. Potassium's got a +1 charge. Bromine has -1 charge. Okay, this is a solid. Do not pull it apart. And this is aqueous, so I pull that apart. So K plus and NO3 with a -1 charge. All right, so this is my ionic. This is called the ionic reaction, the full ionic. Now what I do is I take out spectator ions. So anything that appears on both sides exactly as is, take it out. So silver, well, there's no silver plus over here. Nitrate. There's a nitrate here. Here's a nitrate. Let's get rid of that. Potassium. K plus, get rid of it. All right, so now what I'm left with is this. AgBr, solid. And honestly, what you could do, instead of going through this, if it's just asking for the net ionic reaction, what you could do is once you predict your products and you balance it, then you can just focus on the solid. That should be your product, and then just pull the ions and the solid apart on your reactant side. So if you like writing out the ionic equation and you do it better that way, do that. But if it doesn't ask for the ionic equation, just the net, you can simply do that. That's a shortcut. All right, so let's look at this one. First thing, we're going to predict products. Do an example. Now, if you watched the previous video, I already predicted products here, so I'm just going to go through that part very quickly. So when we have this reaction, we're going to make potassium bromide and magnesium hydroxide. And we need to balance really quick, so 2 goes here, 2 goes there. Okay, so now I'm balanced. And again, if you're still having problems predicting, I advise you go back and look at the double replacement reaction video. All right, so now we have to predict, does the reaction happen or not? Well, let's look. We've got potassium, which is group 1, so this means it's soluble. So that's aqueous. And magnesium hydroxide. Well, hydroxides are usually insoluble. Let's actually go back and look at our rules. Hydroxides are insoluble except when they're with group 1 or ammonium. So group 2 is magnesium. Magnesium's in group 2, so that makes it insoluble. So this would be a solid. So we have a solid here. So the reaction does happen because we have something that's insoluble. So now what I'm going to do to make the net ionic reaction, I'm going to break apart all the things that are aqueous. And you're going to make sure it's balanced as you do this. Okay, so that's why it's important to balance first. Aqueous, we're going to break it up. Well, it's going to break apart into potassium ions and hydroxide. So there's 2 potassiums. And there are 2 hydroxides. All right, so now this is also aqueous, so pull it apart. Magnesium, you've got 1 of those. And bromine, you have 2 bromide ions. Don't forget charges, don't forget to balance. So you've got 2 of those, so you should have 2 here. All right, so now go to our product side. This is aqueous, so pull it apart. We've got 2 potassiums. And you've got 2 bromides. Well, this is solid. Leave it apart, or leave it together. All right, so now everything that's on both sides will get canceled. So K+, cancel. OH is not on both sides. Mg is not on both sides, but Br is. So now I can write my net ionic. So it's 2 hydroxides plus magnesium. All right, and that gives me magnesium hydroxide. And that's my net ionic reaction. All right, so now let's look at another one. When we predict products here, we're going to get ammonium chloride and also zinc sulfate. All right, so I know ammonium should be soluble. Everything with ammonium is soluble. So let's go back and look for a rule about sulfates. Okay, so sulfates are usually soluble except when they're with these elements here. So silver, strontium, barium, lead, and calcium. So usually sulfates are going to be soluble, and zinc does not actually have or zinc is not listed here as one of the exceptions, so that means that zinc sulfate is actually soluble. So we have two products here which are soluble. That means there's no net reaction. So these are our products. This ammonium is soluble, so that's aqueous. And then this is also aqueous because they're both soluble. Since they're both soluble, what ends up happening is they just, once they form, the water pulls them apart again. So that means that they're not really being made. So there's no reaction here. There's no net ionic reaction to right because there's no reaction really happening. You made two soluble products, which means no reaction happens. All right, so let's look at this one. So with this one, I'm going to make aluminum hydroxide and lithium chloride. Well, I know anything with group 1 should be soluble, so that's aqueous. And then if I go back and look at my rule for hydroxides, usually hydroxides are insoluble except for with a few things, and aluminum is not included here. So this is going to be a solid. So the reaction does happen. Let me make sure I'm balanced. I have 3 chlorines, so I'm going to put a 3 there. 3 hydroxides, that fixes it. All right, so this is my balanced equation. Okay, I can do this 2 different ways. I can make the ionic equation, or I can just focus on my solid product. Now that I've balanced it, I can do that. So I'm going to show you the shortcut, and then I will show you the long way, and then you can decide which way you like. So the shortcut method would be to say, okay, this is my product right here. And of course, you have to do this with a balanced equation. Okay, so that's the product I'm going to make. That's my net ionic product. So what I can do is I can say, okay, well, what does it take to make this product? Well, it takes an aluminum ion, and it also takes 3 hydroxides. And that's my net ionic reaction. But if you don't like that and you don't see that right away, you can always pull everything that's aqueous apart. And let's do that really quick. And then make the net ionic reaction that way. So aluminum chloride, it's aqueous, so I'm going to pull it apart. Aluminum's plus 3. Chloride, it would be this. There's 3 of them. Make sure that you put that there. There are 3 lithiums. And there are 3 hydroxides. Well, this is solid. I leave it alone. And then this is aqueous, so I'm going to pull that apart. So 3 lithium ions. And I also have 3 chlorides. So everything that's on both sides, take it out. Aluminum's not on both sides. Chloride is, though. I can take that out. Lithium is, so I can take that out. And hydroxide's not, so it's going to be this. So again, that's just my net ionic. It's just a different way of doing it. So that's a longer way. All right, so let's talk about a special type of double replacement reaction. It's called a neutralization reaction. So when an acid reacts with a base, you're going to form a water and a salt, which is any ionic compound. This is called neutralization, and then that's because an acid will have a pH of below or something below 7. A base will be above 7. So you'll have a pH below 7 and above 7 before, and then afterwards you make water, which is a neutral substance, which has a pH of 7, which is why it's called neutralization. So anytime that we have an acid-base reaction, this is the real reaction that you have. This is the net ionic reaction. You have hydrogen ions being added to hydroxide ions to produce water. And water, it's not a solid, so we're not looking for a precipitate here. We're looking at the production of water. So you still have a reaction happening, It's just instead of making a precipitate, you're making water. So that's the difference between a neutralization reaction and the regular precipitation reactions we've been looking at. This is the net reaction for all acids and bases. All right, let's look at something else. Let's look at the calculation of ions. So I want the concentration of all ions in a 0.5 molar solution of calcium nitrate. So let's go ahead and make the ionic equation when it dissolves into water. So when it dissolves into water, it's going to make calcium ions and also nitrate ions. We'll make 2 nitrate ions though. All right, so I want to calculate the concentration of this. So I want all the ions. Well, I have 2 ions. I have this, and then I have this. So I know that I have 0.5 moles per liter in this solution of calcium nitrate. So I'm starting with 0.5 moles because I have 0.5 moles here. It's asking for the concentration, not the amount. So I can assume that I have 1 liter of solution here. So I have 0.5 moles of calcium nitrate. Well, I can use my reaction now to figure out the amount of each ion. Well, for calcium versus calcium nitrate, it is a 1-to-1 ratio. So 1 mole of this is equal to 1 mole of that. So it's a 1-to-1 ratio, so my concentration here should just be 0.5. So 0.5 moles of calcium ions. All right, so do the same thing here. Let's get my moles of nitrate. Well, in this case, I have 1 mole of this for 2 moles of nitrate ions. So it's going to be 0.5 times 2, which would give me 1 mole per liter. So there should be twice the amount of nitrate as calcium nitrate was put in.